You're now going to learn details about AWS Lambda. First, it's important to get more context before you dive into the Lambda service itself. And we must define some terminology, specifically serverless computing. Serverless computing is an approach to development that enables you to build and run applications and services without needing to think about servers. Serverless applications don't require you to provision or to scale or to have to do anything with regard to the server management. There are two main advantages to building these kinds of serverless environments. First, it enables developers to direct their effort and focus on application functions. And second, it means that SysOps administrators don't need to worry about managing and operating servers or runtimes, and instead, they only need to deploy and monitor the serverless applications. AWS offers many compute options. There is Amazon Elastic Compute Cloud, or Amazon EC2, which provides virtual machines. There are also container solutions like Amazon Elastic Container Service or Amazon ECS. And serverless computing is the third approach to compute, with the advantage that it doesn't require the provisioning and managing of servers. And that brings you to AWS Lambda. AWS Lambda is a serverless computing service. You can run code for virtually any type of application or backend service. You only need to upload your code, and Lambda takes care of everything that is needed to run and scale your code with high availability. You can also configure your code to be automatically triggered by other AWS services, like Amazon Simple Storage Service or Amazon S3, or Amazon CloudWatch events. Lambda code can also be invoked directly from any web or mobile application, and you only pay for the compute time you consume. There is no charge when your code's not running. Yet another advantage to Lambda is that you do not need to learn any new languages, tools, or frameworks. You can use any third-party library, even native ones. Lambda includes support for Java, Node.js, C#, Python, and Ruby. Take a minute to review the key features of Lambda. First, it manages all the infrastructure to actually run your code. You never need to update the underlying server OS or worry about resizing or adding new servers as your usage grows. And next, the administration is automated. You upload your code, and Lambda runs your code with high availability. Lambda has built-in fault tolerance. It maintains compute capacity across multiple availability zones in each region, and it provides high availability for both the service itself and for the functions that it operates. In terms of scaling, it's fully automatic. That is to say, it automatically scales to support the rate of incoming requests. And you don't need to configure anything. There is practically no limit to the number of requests your code can handle. Also, Lambda can start as many function occurrences as needed without lengthy deployment and configuration delays because your code is stateless. What about more complex environments and workflows? You can orchestrate multiple Lambda functions for complex or long-running tasks by building workflows with AWS step functions. You'll learn more about the details of AWS step functions later in this module. In terms of security, Lambda integrates with AWS Identity and Access Management, or IAM. On the back end, Lambda itself runs the code in a virtual private cloud, or VPC. And optionally, you can also configure Lambda to access resources inside your own VPC. And optionally, you can also configure Lambda to access resources inside your own VPC. And you have full control of what resources can be accessed using custom security groups and network access control lists. In terms of cost, you only pay for the requests that are served and the compute time that is required to run the code. And in terms of granularity, billing is metered in increments of 100 milliseconds, which helps make it cost-effective if you scale from just a few requests per day to potentially thousands per second. And finally, Lambda offers a flexible resource model in that you actually choose the amount of memory you want for your function. And then a proportional amount of CPU, network, and disk I/O are automatically allocated to match that. Now, let's look at the process for developing and deploying a Lambda function with dependencies. First, you must define a Lambda handler class in your code before you upload it. The handler specifies where Lambda can begin running the code. And next, you create the Lambda function itself in AWS. This can be thought of as that Lambda function's configuration in AWS, including the code that will run and any other configuration details and resource requirements. Then, you must configure permissions to access to any AWS-controlled resources using IAM and IAM roles. Remember, though, that both AWS-controlled and other resources, like EC2 instances, might also need access granted at the networking layer. For this purpose, security groups and network access control lists, or network ACLs, can be used. And finally, you upload your actual code. Here's an example situation. In this example, you want to reduce your Amazon EC2 service usage. You decide you want to stop instances at a predefined time. Maybe you want to stop EC2 instances at night when less capacity is needed. You also want to start the instances up in the morning before the workday starts. You could configure Lambda and Amazon CloudWatch events to perform these actions automatically. The diagram illustrates what happens at each step in the example. First, an event is scheduled through the CloudWatch events to run a Lambda function to stop your EC2 instances at, for example, 2200 GMT. Next, the Lambda function is triggered and run with the IAM role that gives the function the actual permission to stop the EC2 instances. Note that if multiple Lambda functions are invoked at the same time, the soft limit per region for concurrent functions is 1000. Now, the EC2 instances enter the stopped state. Later, at 5 o'clock GMT, another event is scheduled through CloudWatch events to run another Lambda function to start the EC2 instances. In step 5, the Lambda function is triggered and run with the necessary IAM role to give it the permissions to start the EC2 instances. And finally, the EC2 instances enter the running state. For more information about creating stop and start functions with Lambda and CloudWatch, search for Start Stop Lambda CloudWatch in the AWS documentation. What if you often need access to the same libraries for your Lambda code, or you want to run code in a language that's not directly supported by Lambda? You can configure your Lambda function to pull in additional code and content in the form of layers. A layer is a zip archive that can contain libraries, a custom runtime, or other dependencies needed for your application. With layers, you have the convenience of being able to use libraries in your function without needing to include them in your deployment package. Layers can also help to keep the deployment package small, which makes development easier. You could potentially avoid errors that could occur when installing and packaging dependencies in your function code. For Node.js, Python, and Ruby functions, you can develop your function code in the Lambda console as long as you keep your deployment package under 3 megabytes. A function can use up to 5 layers at a time, but remember that the total unzipped size of the function and all layers can't exceed the unzipped deployment package size limit of 250 megabytes. In addition to creating your own layers, AWS publishes layers, and so do other AWS customers. They support resource-based policies for granting permission to specific AWS accounts, AWS organizations, or all accounts. In terms of function run environment, layers are extracted to the /opt directory. To add layers to a function, developers use the update function configuration command. You'll get the chance to work with Lambda in the lab environment. For more details about Lambda layers, search for configuration layers in the AWS documentation. In closing, note that Lambda limits the amount of compute and storage resources that you can use to run and store functions. And as of this recording, the maximum memory allocation for a single Lambda function is 3 gigabytes. There are also limits on concurrency and on package size, which is currently 250 megabytes as of this recording. If you're troubleshooting a Lambda deployment, keep these limits in mind. And to get up-to-date information for the current Lambda limits, search for Lambda limits in the AWS documentation. Thanks for watching, and see you in the next video. Next, you'll review APIs and the representational state transfer architecture, which is also known as REST architecture. Most people who use computer software are familiar with using a graphical user interface, or GUI, to interact with the software. And the AWS Management Console is a GUI for interacting with AWS services. Application programming interfaces, or APIs, make computer software accessible to developers via code so that they can build software programs that interact with other software programs or computer infrastructure. APIs work as an intermediary for applications to communicate with each other, and this communication is initiated with something known as an API call. An API call is a message that is delivered from one application, which is sometimes called a client, to another application, which is sometimes called a server. The message being sent is referred to as a request, and the software receiving the request then returns a response to the requester. Like how you can use software services through a GUI, some software programs enable you to do the same tasks through an API. Be aware functionality may change when using the API. If you ever use the AWS Command Line Interface, or AWS CLI, then you made a request to the public APIs of AWS services. It is helpful to have standardized design guidelines for implementing APIs, and some APIs follow the principles of representational state transfer, or REST, and these typically communicate over HTTP. Web-based APIs that follow REST design principles are referred to as being RESTful, and it is a popular API design that has mostly replaced its forerunner, Simple Object Access Protocol, or SOAP, as the standard for web services. You'll explore the REST design principles next. REST follows 6 design principles. First, there should be a simple and uniform interface for the client to access the server, and a request should be made to a single endpoint, or URI, when it interacts with each distinct resource that it's a part of the service. But be aware that the interface itself doesn't define the structure of what's returned when the client makes a request. Next is that RESTful services are stateless. Stateless means that the server doesn't track the request that the connecting client made, or what step the client might have completed in terms of a related series of actions. In fact, any session information about the client is only known to the client itself. The server doesn't know about the state of the client, and the client doesn't know about the state of the server. Also be aware that REST clients should be able to cache the responses they receive from the server. Also, RESTful services support what are called layered systems, where the client might connect to an intermediate server instead. This design has many benefits in enabling the REST server to be distributed over multiple compute resources. This supports fan out from a load balancer because the load balancer could be the intermediate server in the situation. One of the final features to highlight is that RESTful services can optionally support code on demand. This means that the server can pass a piece of executable code, such as some JavaScript, to the client. This feature is designed to extend the functionality of the REST client. Some of the benefits of using code on demand in RESTful APIs include client-side validation, asynchronous lightweight subrequests, and the dynamic processing of additional message semantics over and above the semantics that are contained within the core media type definition itself. At this stage, though, code on demand is considered optional because it's not widely adopted across developers. Now you'll go deeper into the actual details of a REST request. A REST request includes 4 components. First, there's an endpoint. Anytime you make a request to a REST server, you must know the endpoint. The endpoint comes in the form of a URL, which is a way for the client to notify the server about the resources it wants to interact with. Next, the request must include a method, and each resource exposed in the REST API supports one or more methods, which include a GET request, where the server is requested to retrieve a resource, a POST request, where the server is requested to create a new resource, a PUT request, where the server is requested to edit or update an existing resource, and a DELETE request, where the server is requested to delete a resource. The next part of the request is a header. The header contains metadata about the request. And then finally, the request includes a body. The body of a request is the actual data that the client sends to the server. A POST or PUT request will typically contain a body. If you invoke a PUT method, you would most likely need to include details in the request about how an existing resource should be updated. GET requests, on the other hand, rarely include a body. Here's an example of a REST request to a RESTful API. The client URL, or curl, tool is a command line tool you can use to get or send files over HTTP or HTTPS. Here, the -I indicates that the response itself should include the response headers. The -X indicates the method that's being invoked, like a post, for example. The -D is commonly used with post or put methods to provide the data or body that is being sent to the REST server. In this case, the data is contained in a file called file.json. And the -H is used to pass header information, which includes the content type that an acceptable response should include. Also note that a request must include credentials for authentication in the header of the request, although these are not shown in the example. The response that you see here is in JSON. The REST API response is important because it tells you if the request was successfully received. You can use the returned HTTP code to know if there were errors and to troubleshoot accordingly. Here are some of the more common HTTP status codes and what they mean. First, 200 indicates success. In this case, the request was received and accepted by the server. 401 indicates a client error or unauthorized. Authentication is required, but the provided credentials were not accepted, or perhaps no credentials were provided in the request. 403 indicates a client error or forbidden. The request was properly made, but the server is not allowing the request. 404 indicates a client error or not found. The resource is unavailable or cannot be accessed. 500 indicates unspecified internal server error. And then 503 indicates that the service is temporarily unavailable. That's it for now. Thanks for watching and see you in the next video. Now that you know about APIs and REST, you are ready to learn about Amazon API Gateway. Amazon API Gateway is an AWS service that you can use to create, publish, maintain, monitor, and secure APIs at any scale. And you're not limited to accessing only AWS resources. You can create APIs that access other web services and any data that is stored in the AWS cloud. API Gateway is designed to handle all the tasks that are needed to accept and process concurrent API calls at scale. These include traffic management, authorization and access control, monitoring, and API version management. And you only pay for the API calls you receive and the amount of data that is transferred out. As your applications evolve and grow, your APIs will almost certainly multiply. And along with this growth, it is increasingly important to monitor and manage your APIs. Conceptually, it's important to understand that the API interfaces that you develop will have a front end and a back end. The front end portion is used by the client applications to make requests. The back end, on the other hand, refers to the parts of the API implementation that communicate with the other AWS services. In Amazon API Gateway, the front end is encapsulated by method requests and method responses. The back end is encapsulated by requests and responses that integrate with the other AWS services. These AWS services provide the functionality that is exposed by the API. One of the main benefits of building an API with API Gateway is to selectively and consistently expose some of your AWS functionality and data to your end-user developer community as part of an integrated and consistent developer experience. This can provide a vehicle for fostering and encouraging a whole developer ecosystem around whatever data and functionality you want to expose, which can lead to new and unforeseen applications. It's possible to integrate API Gateway with Amazon CloudFront to take advantage of the worldwide network of edge locations, which provide your end users with the lowest possible latency for API requests and responses. API Gateway also helps manage traffic through throttling, so that back-end operations are better at withstanding traffic spikes. After the API is deployed, you can visually monitor calls to your services via a dashboard for accessing performance metrics and for simultaneously running multiple versions of the same API. This enables you to quickly iterate, test, and release new versions while maintaining access to previous versions at the same time. From a security standpoint of view, IAM can be used to authorize access to your APIs, And if you already use OAuth tokens or other authorization mechanisms, you can use Lambda to run a Lambda authorizer to help verify incoming requests. API Gateway integrates with Lambda for the creation of serverless APIs. And the workflow would involve first creating REST APIs using API Gateway, and then allowing your mobile and web applications to call publicly available AWS services through the code that you run in Lambda. After you create RESTful resource-based APIs in the API Gateway, you then use the data transformation capabilities to generate the requests in the language that your target services expect. JavaScript is run in the browser, and it sends and receives data by communicating RESTfully with API Gateway. The data sent through API Gateway uses the backend API that was built with Lambda. Take a moment to review the first two components of the web application in the diagram. First, Amazon Simple Storage Service, or Amazon S3, hosts static web resources. These resources include the necessary HTML, CSS, JavaScript, and image files, which are all loaded in the user's browser. Then, Amazon Cognito provides user management and authentication functions to secure the backend API. Here are the other two components of the application. JavaScript is run in the browser, and it sends and receives data by communicating RESTfully with API Gateway. The data sent through API Gateway uses the backend API that was built with Lambda. Amazon DynamoDB is the fourth component, and it provides the persistence layer so that the Lambda function used by the API stores data in the DynamoDB database. That's it for now. Thanks for watching, and see you in the next video.
Welcome to this Amazon Elastic Container Service, or Amazon ECS, Docker container demo. So I'm in the AWS Management Console. I'm actually going to open up Window and going to run through, this is for the Elastic Container Service that allows you to Docker container using Fargate. And Fargate allows you to have administration and everything done on the background by AWS rather than you having to create the cluster and administer the cluster if you were doing it by yourself. So we're actually going to use the sample app, as you can see here. And if you can look, the task definition, it's a blueprint for your application. So it talks about this being a first run task definition. It'll create an AWS VPC. It's new, and we're going to be compatible with Fargate. Talks about the task memory and the task CPU needed. What this does is this sample app includes the HTTPD service, or basically the Apache web server. And that's what we'll go ahead and test out and install. So when I go ahead and click Next, I can go ahead and define the service. So I can define the number of tasks. In this case, there's one. And if I wanted to add an application load balancer, I could. Please note that the security group is created to allow all public traffic to access our service on the container port specified, in this case, HTTP or port 80. We can give the cluster name. I'm going to call this test. And I'm actually going to spell it all, and then it automatically creates a new VPC ID, and it creates new subnets. There's one review, so we can edit our task definition, our service, and our cluster prior to going ahead and creating it. Go ahead and click Create. And now we'll give it some time. So there are 9 steps that need to take place. It's already created the cluster task and is looking at the task definition, and it's in the process of creating the rest of the Elastic Container Service resource. We'll just wait a few moments here. Shouldn't take long. All right, we're back, folks. As you can see, I have all complete on all 9 steps. Had I not chosen to use Fargate, had I chosen to just do EC2, I would have to create an EC2 instance. I would have to install Docker on it, and then I would have to go ahead and create my container for this particular application. Notice this is just a simple way for me to go ahead and create a container. I didn't have to worry about the underlying infrastructure. I don't now have to worry about updating the EC2 instances with new packages. All of that's going to be taken care of by AWS. If I was managing my own Docker containers on an EC2 instance, new packages come out, I'm going to go ahead and have to install those. So by using Fargate, you're letting a lot of the administrative capabilities be handled by AWS, and you can focus on running your containers and making sure those applications are used. So we'll go ahead and click View Service. And here is my test cluster. See, it's enabled. You can see its launch type is Fargate. It would say EC2 if it was not. If I had chosen the other way, the more manual way of deploying this. I'm going to go ahead and click Tasks. And it shows me that it is running. And I'm going to go ahead and click this task. And actually, this will open up more details about it. And what it has done here is it has given my container, remember, it's a web server, an IP address. So I'm going to go ahead and copy that public IP address. I'm going to add that public IP address here. And it comes up and shows me that it has deployed successfully in that container. So this proves showing us the ability to go ahead and use Fargate to rapidly deploy containers with applications and get those applications up and running. Thank you very much, folks. Have a great day.
Now it's time to review the module and wrap up with a discussion of a practice certification question. In summary, you learned the purpose and function of AWS Lambda. You also learned how APIs expose programmatic functionality to clients. And you can now describe the characteristics of RESTful APIs and their uses. You also learned about the benefits and function of Amazon API Gateway and how API Gateway coordinates API calls with other AWS services. You learned in detail about the purpose and function of containers, and you also learned about the 3 different AWS services that support container usage. And finally, you finished this module by learning about the purpose and function of step functions. Good work. You'll now look at a sample certification question. Take a minute or two to review this sample question, which could be on a certification exam. Now look at this sample scenario and look for any keywords that will help you identify the correct answer. Here, the keywords in this scenario were highlighted. Think about the answer options. Keeping the keywords in mind, look at the answer options and try to rule them out based on the keywords. The best solutions in this case are B, D, and E. Now it's time to complete the Module 5 Challenge Lab. Create Lambda function to send email reports. Thanks for watching. See you in the next video.
Welcome to Database Services on AWS. In this module, you will learn about different managed database services offered by AWS. You will learn about the capabilities and benefits of Amazon Relational Database Service, or Amazon RDS, Amazon Aurora, and Amazon DynamoDB. You also will learn about the AWS Data Migration Service, also known as AWS DMS, and the accompanying AWS Schema Conversion Tool, sometimes called AWS SCT. By the end of this module, you'll be able to differentiate the types of managed database services offered by AWS and identify their recommended use. You will also be able to identify factors that you should consider when you select a database engine. You will be able to describe the purpose and function of Amazon RDS, Amazon Aurora, and Amazon DynamoDB. You will also be able to describe the main features and benefits of each database service. Finally, you will be able to explain the benefits of the AWS DMS and the capabilities of AWS SCT. Let's get started.